Yes.
So if we were to run the playgrounds again, it goes in 3. If I was to run it again, every time it might change, it might not. There's no guarantee. Right now it's in index 2. So to go back to our drawing here, first we said Alex is in index 0. Okay, that's fine. We were able to get the index where Alex goes by using the ABS, which we spoke about earlier. The ABS basically gives you a positive value regardless of if the inside operation is negative or not. It gives you back a positive value. So here we say in the string, which is Alex here, the key, get me the hash value. The hash value here is a hash function, a built-in hash function. Based on the bucket count, put my key in one of the indexes of that bucket, right? And we said dictionaries, we don't know dictionaries are not sorted. So we cannot in any point in a dictionary index into the dictionary saying, oh, get me the value at index 0. Because we see exactly what just happened. Every time we rerun the code, the index changes. So there's no guarantee of knowing where Alex is. The only way I could access it is via the key, right? I say dictionary key, give me the value for Alex. I don't say dictionary subscript 0, give me that value at 0. Is everybody with me so far?
Yes.
All right. Cool. So this is just a overview of what hash functions are, what the hash value gives us, and some of the logic we'll be using. Was there a question? Some of the logic we'll be using in getting the index of where Alex goes. Okay. A scenario could be, I might have a string that happens to be in the same, let me actually decrease the count. Let's see if that's gonna happen. So let us decrease the count. So our array has 4 indices. Let's change it to 2, for example. And let us get a different hash value or same hash value, doesn't really matter. I'll say index 1 or index 2 here. I'll say index 1 here. I'll change the string to Brandon. Let's get some more. Index 3. Let's make this a hard, and let's make one more. Here we have Tanya. Let's actually just change those. Alex hash value, Brandon hash value, hard value. Actually, it should have been indexed, but that's fine. Tanya. Just make that easier to read, actually. Index, Brandon index, and Alex index. Okay, cool. So we have some indices here. Let's see what's happening here. So let's say Alex index here. Bring that. So Alex, Brandon, Ahad, and Tanya. So if we were to run the code here, what do we get? So if we were to look at our console, we see we have 3 names using the same index, right? So Alex, Brendan, and Tanya are using the same index. So if we were to go back to our whiteboard here, we have Alex. Well, there's a problem. Anybody sees the problem here so far? Alex is already taking up 0.
Yeah, so they're all going to be in 0?
They're all going to be in 0, so that's not going to work because it's going to override it, correct?
Okay.
So in hash table parlance or in hash table terminology, this is known as a collision. So we have Alex, we have Tanya, and we have Brendan, all trying to go into index 0, right? So this here is known as a collision, right? So here we have 3 keys trying to go inside the same index in our buckets array. So that's a collision. One of the ways you could solve collisions in hash tables is what's known as chaining. Right? Chaining, you could use a linked list, you could use an array. In our example here, we'll use an array. So basically, in our buckets array, you could have a chain of key value pairs. So for example, if you have a mini who goes, if we were to do a mini's hash value index here, a mini, if we have to do the hash value of a mini and a mini happens to go in index 3, right? And we do Tiffany, we do Eric, and they're all in index 3. What we do with chaining or with a collision is create a series of chains, right? Or links. So here I would have a mini. Let's just give it, let's just give them ages. So 21, and we have Tiffany, 19, and then we have Eric, who is 25, right? So here we have chaining. So this is chaining, right? So no longer are we gonna have collisions. Anytime we get a next value at index 3, we just add to that chain. Any questions so far? Any questions so far?
Couldn't you just have increased the size of the array?
Yes, we can increase the size of the array, but now if we increase the size of the array, that takes up memory. That's gonna make our hash table slower, and it defeats the constant access of a dictionary, right? It becomes just a next array that you put your values in. You want to keep your hash table as small as possible and increasing it only when you need to. Jahid? I mean, sorry, Juan?
Okay. So you preferably just want it all in one, all chained together.
Yeah, chain together, you have a hash value, it goes into 3. We're not gonna redo a hash value to put it in a different bucket because that's where it goes. It goes into 3. We wanna keep our chains short as well. So what happens is dynamically, the hash table will grow and shrink, right? So your hash table could grow and shrink dynamically based on the capacity of it or based on how many keys you have in there.
All right, dynamic hash table makes sense.
Yeah.
But why would it affect the constant time exactly of reading?
Because here we just have an array here, right? We just have an array here. You're trying to put in key value pairs, right? Key value pairs, right?
It's just because we're
so if you
making
have
the dictionary rather than just using a dictionary that.
Exactly. You're making a hash table here. We're not making a dictionary. If it was a dictionary, we just use it. We just use the built-in Swift dictionary. But here we're not using the built-in. We're not using the built-in Swift dictionary. We're making a hash table from scratch. That's how a dictionary works behind the scenes with more performance enhancements, of course. But that's the basic structure of it.
I see. Cool. Thank you.
Okay. There was a next question here. So it grows and shrinks based on the count or the count of keys you have. Because that chain itself, you don't want to get it too long either, because that's going to also slow the performance of your hash table.
So preferably you'd want like a balance, like.
Exactly.
I have a question.
1 second, I just want to talk about one more thing before I. So the way you figure out the optimization of your hash table is using what's known as a load factor. Let me just put load factor in here. load factor. So the load factor will determine, based on the space you have left and the keys you have, you'll determine what's your load factor. The closer your load factor gets to 1, for example, the closer it gets to 1, that means you need to get more capacity for your hash table, right? But load factor, we won't get into the implementation of it today, but just know that the growing and shrinking of your hash table is done based on the load factor of the hash table, meaning how many keys do I have and how much space do I have left? Do I have to increase my buckets or can I decrease my buckets? Like in your case, Juan, you were talking about 100 indices, right? If I'm only using 2 of those, the performance will be very slow on that, right? Or the memory I'm taking is very big. I don't want to take extra memory I don't need. So that goes back into like space complexity and everything. Don't get memory you don't need, right? So
I see what you mean. Okay, so would the load factor be the more, I guess it's what's the controlling,
how it grows
has more
and
influence.
exactly.
Okay.
Exactly. The load factor has to do with, do I need to get more more space in my buckets or can I shrink? Because I'm only using 5, but I have 10. Can I shrink that up? Can I shrink that down? Does that give you some more clarification?
No, yeah, it does. Thank you. Thank you.
Chelsea?
Yeah. Hello?
Yeah, go ahead.
Yeah, the question that I had was, so you added the age. So is our ability to chain based on the object having more than one property, or like how would it know?
I just put the age there because it's key value pairs, and I realized we did not have a value for our key. So I just said it's going to be like string int, where int is just an age, for example.
Okay.
Because in the dictionary that we use from unit 1, it's key value pairs. In that case, the value would just be an age, or an integer, sorry.
Okay.
Right, so for example, a mini here would be represented as a string and an integer, correct?
Yeah.
So that's key value pairs. The string here would be the key, and the value would be the integer. Yes?
Yes.
All right.
Thank you.
Very good. So those are the key terms. Please write those down because we've gone through so many structures that sometimes we lose which one is which. The important things to know here is collision. The reason why I'm really talking about hash table today is so we know what a collision is. And a collision you get when you attempting to insert multiple keys in the same index, right? So if you have to write one thing down, that would be the thing I would write down today. What's a collision? And there's multiple ways outside of just chaining, right? Chaining is one of the ways, but there's other ways as well to resolve collisions, right? But the one we'll be implementing today is chaining, right? So we'll have basically like an array of arrays. So here we have the buckets array outside here. And over here, we'll also have an array. Where is my? And here we'll also have an array of basically key value. We basically have an X array of key value pairs. This is also going to be an array. Okay, so it's going to be an array of arrays, array of buckets, and also an array of key value pairs. And the way you optimize your dictionary, or sorry, the way you optimize your hash table is by using the load factor, as I said. And that determines if you want to increase the size or if you want to decrease the size. And we also saw hash functions here. This is a hash function. Right? I haven't seen too many of those asked in the interview, but just knowing what a hash function does for now suffices. But as time does permit you, take a look at writing your own hash function. But as far as like being more optimized than Swift, the hash value we're getting from Swift is definitely more optimized than anything we'll probably write. All right, cool. Any questions before we move to coding this? Any questions?
I'm just curious why collision would occur. It's probably because we're doing modulo bucket.count, but if a hash value returns a unique value for each piece of data every time it's ran, why we would get a collision in this instance?
Got it. So you get the collision because you're taking the mod of the bucket count.
Okay, we're basically simplifying everything, and it's just there's not enough options. The hash values are probably unique every time.
Yeah, they are unique.
But the absolute value of it is not.
Exactly. The absolute value with the mod operator on the count of the buckets.
Understood.
Right? Because you want to put that key in one of the indices of the bucket. And
right.
No matter how unique your value is, once you take the mod of the bucket count, it might happen that there's a collision there.
Gotcha.
Mm-hmm.
Thank you.
Very good. Okay. Any other questions with the theory behind all this? At the end of the day, we're just recreating dictionary, but knowing how it works, and then the key terms here, because you could get asked things like, "What's a collision?" Right? And it's going to be not good of me to not talk about hash tables and collisions there, right? So that's very fair game for interviews. Or what's one of the ways you could solve a collision? All right, so let us go implement it here. I leave all that here, that's okay. Leave all that here, and let's go down here. So implement, oh, we don't have time, 11 o'clock already. Implement HashTable. We'll call it HashTable. What do we know about hash tables again, or dictionaries? What makes them unique?
You can't repeat the key.
You can't repeat the key, so it's unique. Very good. So here we'll say, we'll call this key. Key needs to conform to hashable. That's the big difference here. And then we'll have some value. Value this. So example, when we get to use our hash table, we'll have some syntax that looks like this. We'll specify during writing our code what the key will be. And again, the key could be string, it could be integer, anything that's hashable. And the value could really be anything. The value doesn't have any constraints on it. The value could be your own type, which is a person. It could be random type, whatever type it is. Okay, and we'll have some sort of capacity here. So how many indices we want, some count value. All right, so let's continue on. So we had this notion of buckets, and we had this notion of key value pairs. So let's start off with the key value pairs. So here I will mark this private. We'll use a type alias. And what is this called? We'll call it element. What's an element? An element is basically our key value pairs. For example, key value, which is a tuple, right? This is a tuple, but we cannot name a tuple. So the best way to name a tuple is using this type alias here. Type alias is we've used that before. I think in unit 3, we used it a bunch of places. Instead of saying like string something, you could give it some sort of nickname or alias. Was there a question? Okay, so here we will say, what's my element? My element will be key. So key value example here. And age is some age, 21. All right, and let me go back to the drawing. I don't want to lose this here at all. So the element, what does the element represent? This is one of the elements. This is an element. Okay. Let's continue. Next. Holding our elements, we said we have an array, right? So we have an array here. I'll also use type alias to represent what the array is. And the array is going to be an array of elements. If I was to go back to our drawing again, over here, this is our bucket. And it's an array of elements. Does everybody see why I put buckets in here? Or bucket, sorry. Bucket represents the chain. Hello?
Yeah.
Yep.
Okay. Let me make sure we're still here. Okay, now moving to the actual buckets array. Buckets array. Okay. And this buckets array is the array of all the buckets, which we have over here. So this array here would be an array of buckets. Okay. It's an array that holds all those buckets. All right. Awesome. So those are our variables. Let's move on to our initializer. What does the initializer look like? Our initializer will take some capacity, how many things we want to store, or be able to store rather. Capacity is some integer. All right. And here, what do I want to initialize? Buckets equal to array of bucket. We'll start off with everything being empty, and the count is whatever the capacity count is. Okay. So for example, what does that look like? If my bucket has, what do we use here? If it has 4, our buckets, if we were to print it out, is going to look like this. 1, 2, 3, 4. It's an array of arrays. Okay. And as we're putting items in there, they'll start getting populated. So I'll have key value pair where key is Tiffany, value 21, and so forth, right? If I have a key that happens to be in that index, it just comes with a comma and whatever the key value pair is. Any questions so far? Any questions?
In this example, is there any reason why the third position in the buckets is filled as opposed to the first one?
So if we do the hash, very good question. If we take the hash value and we take the ABS on the count, and it happens to be in index 2,
okay,
this is where it's gonna go.
Gotcha. For the same reason as earlier. Understood.
Exactly. Very good. Okay, cool. So let's start moving to the key functions we need to write. First one, return function or method to return index where key will be stored. Write a method to search for key, or to search for a value, to search for a value given a key. We'll write method to update a value for a given key. What's the next one we're gonna write? Method to remove value or remove an element at a given. Okay, cool. Let's get at it. So method one, very similar to what we did earlier with the hash value and the mod count. We'll do it here. We'll write a function. We'll call it index. It takes a key for key, whatever key the user brings in, and key is of type key. And here, what are we returning? We're returning some index, so some integer. Method to return index. Very good. Anybody want to walk me through what we're writing here? It's very similar to the pseudocode we wrote earlier to get back what index the key goes into.
Would be let index assign key dot hash value modulo
Index key dot hash value mod
modulo bucket dot count.
bucket. Very good. Buckets dot count, right? Yes. And what are we doing now? We got to return something, right?
I probably want to return that index.
Return index. And what happened to, we could get, what else, what's missing here?
Oh, the absolute value. You got to wrap
Absolute
it
value.
ABS parenthesis and close
Very
it.
good, very good. So here, this is what we have. And since we have just one thing happening, we could just say return here. Very good. Thank you, sir. So this here returns, it gives us what index in the buckets array that this key goes to. Okay, everybody with me?
Yeah.
All right, awesome. So this is the first method here, great. Next method, we want to be able to search for a value for a given key. So function, we'll say value for key, some key. If we got to return a value, what am I returning here? What data type?
Value?
Value. Is it just value? Is the value always is it always gonna be found?
Optional.
Optional, very good. Because it could not exist, right? But there's a possibility that value doesn't exist. Very good. All right, so now we're looking for a value for the key. First, let's see where the index is. So in that case, we'll just use our index function we just wrote. It's asking for a hashable type. We just passed in the key. Awesome. So now let's use a for loop to go through and find if it exists. So for element in buckets index, right now you're going through, right now what are we going through? We're going through, let me go to the iPad, I'll be right back. Right now we're going through our chains. So if the index is at 3, right, I'm going through my chain here to see where is that key. Everybody with me?
Yeah.
Okay. So here, element, if element dot key, the current key I'm looking at, if the current key I'm looking at equals to the key I'm searching for, then we found the value. So just return element dot value. And if all that failed, if we didn't find anything, what should we return here?
No.
Nil. Return nil. Okay. Awesome. So we've written the method to find the index where the key goes. Now we've written a function to go ahead and go through the chains and find out if the element exists. If the element exists, we just return the element. If it doesn't exist, we return nil. Okay. Moving on to updating a value, right?
A little bit.
Say that again?
Can you scroll up a little bit?
Oh, yeah,
Thank
yeah,
you.
yeah.
Oh, okay. Got it.
Cool.
Thank you.
All right. So method to update for a given key. So function, here we're going to be mutating some our data structure. So we're going to say mutating here, mutating function, and what's the name of my function here? Update. Update value.
Alex, do we need an else for the function of
You mean here like else something?
else return? Because isn't it going to return no regardless, or am I reading it wrong?
No, so you have a function, the first return, if it encounters that return, what happens?
Oh, nothing. Okay, yeah, never mind.
No, it's good. So update value, some value for key, some key. Okay. Most of the functions we have here will be relying on this index utility function we wrote in order to find out what index we're referring to. So same thing here applies. So self.index for key. So now we want to update some value, right? Maybe the value exists, maybe it doesn't, but we want to update some value. So now we're going through the chains and we want to update one of those indices in the chain. So that's why I'm using this index I here and element in buckets, index. How do I get access to an index in an array? How do I get access? Enumerated. So now on the array here, I say enumerated, and it gives me access to the index. Cool. All right, so here, if element key equal to the key, right? That means the key exists, or right, the value exists for that particular key, right? There is a value. So we'll get the old value. The old value is element.value. And now we want to update the current value. Buckets, index. How can I update the value right now? I have my array. I want to update just the value, not the key, just the value. How do I get access to the value here?
So just put equals? No, that's for the...
We're going to be passing we'll be assigning some value to it.
Old stuff? No, never mind, I'm not following.
No, that's okay. We have an array, that's just an array. That's the buckets array. Why we have that I here? What's the value of it? Picture you have a 2D array, which we do have here. How do you change a value in a 2D array?
You index I.
You index I, very good. So here I'm gonna index I that value. Thank you. Because keep in mind, we have an array of arrays, which I said earlier. If you have an array of arrays, you want to change the value on it, right? It's double indices or double subscripting, sorry. The first subscript represents the outer array. The second subscript represents the inner array. In that case, our chain array, right? On our chain array, now we have an element. This represents an element. An element has a value and it has a key. We just want to change the value of it, so we dot value on it. Where's that value coming from? Well, the value is coming from this value here, right? Everybody with me?
Yeah.
Okay, cool. And as with all dictionaries, you could return the old value that you just updated. So here we return the old value. Well, we need to change this as well. Value. Make sure you update your return, your function to return a value, or return value, optional. All right, cool. So all that is good. This only works if the element, if the key has a value. What if it doesn't have a value? Well, what are we gonna do now? If it doesn't have a value, so here, we get here if the key, if there's no value. We get here if there's no value. Okay, so if there's no value, what do we want to do? Well, we have the buckets array index. Now we want to append, because we didn't find anything, right? It's empty at this point. So now we just want to append. We want to append a new element. And keep in mind, you see how element is here? Element is what? What data type is element?
A tuple?
It's a tuple. Very good. So anything we put in that append function needs to be a tuple. Okay. So here we have our two open parents. I'll put the next two open parents, and I'll put in my key, which is just key, and my value, which is just value. Right? I have to make sure I got the context correct before I do this. Here is a tuple. I'm expecting a tuple, so this is a tuple. And next, I could just return nil, because this is new. The reason why we return a nil, to signify there wasn't an existing value. Okay.
I'm just curious why we're returning the old value or nil here.
Just to know the value we changed, we updated.
Okay.
Yep, because normally in dictionaries as well, you could get the old value that you replaced, because maybe you want to do something with that old value.
Fair enough. And if you're replacing the value, you already
Here.
have that stored. So you may, if you need that, you could just look that up anyway. Okay.
Exactly. Couple of things I want to update here. There's a count we could probably keep track of. So go to the top and create a new private variable. Hold on time, we're good on time. Create a new private variable, call it count. Count is 0. Okay. I want to show us something. I don't know if I've shown it before. Maybe I did, maybe I hesitated. But here, this is private. I could only access it within this particular object, correct? Yes, no, maybe?
Correct.
Yeah.
Okay. What if I want to access this private count from outside of my struct? How is that possible? Well, we could do a couple of things. I could make some sort of like computed property. I could do a function returning some count, or I could use this syntax here. So now my setter is the only one that's private. My getter is public. So getter is public. So anybody could get my count by just saying hashtable.count or whatever, right? But nobody cannot set my count, right? Except myself. So setter is private. So this is the syntax for it. Everybody with me?
Yeah.
Okay.
Yep.
It's a very powerful tool, right? You could just use this and know that nobody can change your value except internally, right? But publicly, somebody could get your value. Okay, very powerful little thing. Okay, so now in our update, we could change the count here. So count plus equal 1, because we like to say dictionary.count, right? So here we also want to say hashtable.count. And here we just update the count. We don't update it here because this is an existing value. Everybody with me? Yes?
Yeah.
Okay, we only update it here because this is a new value. All right, great, great, great. Any questions about our update function before we move on?
Alex, I have a question about the syntax for setting to set.
This guy?
Yes. Can you also use that, like if you wanted to make get private for whatever reason?
So
would you
nobody
just write private?
I think it would just be private at that point. Like you mean nobody can get your value?
Right, but they could set it.
I don't think that doesn't exist. It only exists for setters.
Okay.
Yeah, because in your case, you just mark it private like that, right? Like, and nobody can access anything. So if they want to set a value, you could just write a function at that point.
Right.
Yeah, I know. It would be nice as well. Okay, so going back here. Good, good, good. Let's go back down. Update, we have remove. Let's go to remove. What's happening? Let's go to remove now. Remove is also a mutating function. Anytime we change in our data structure, when I say data structure, I'm talking about this data structure here. Anytime we change in those things there, and we inner struct value type, we need to mark our functions as mutated. If it was a class, it wouldn't be, right? So now we have our method for removing function. Let's call it remove. Remove value for key. Key is of some type key. Also want to return some value, optional value. Okay. Also want to get our index here, self.index for key. Okay, for element in our buckets array, if the element exists, we just want to remove it. Okay, so buckets, index, well, I need to remove some index, remove, but what's that index? What am I removing here? Can anybody help me? I need to get access to the thing I need to remove. Because right now we're going through the chain, and I want to remove that index at that particular chain position. How do I get access to this index? Oscar?
I'm not too sure, to be honest with you.
It's very similar to the update function. We're missing some syntax to get us access to the index of the array that we're going through. We have that index, which is the outer array, but now we want to have the inner index. How do I get access to it?
Maybe use enumerated like you did.
Okay, so enumerated will give us access to our inner index, right? Thank you, sir.
Yeah.
Okay, cool. So we removed that. This is good. And here we could just return element.value. And for our count, we could decrement our count because now we're removing a value. If we did not find it, we just return nil. Okay, so this is remove. Search for it in our chain. If we find it, remove it, decrement the count, return the value we just removed. If we don't find it, just return nil. For the most part, we have most of the functionality of our hash table ready to go. So we could actually test it out. Any questions, any code errors so far? We good? Okay, let's test. the hash table then. And here we'll say var hash table equal to hash table. Somebody walk me through the syntax. Tiffany?
Yes, Alex.
Hello.
Hi.
I want to construct the hash table where the key is string and the value is an int.
Okay.
And capacity is 4.
My nephew is here, so I'm taking notes, but I'm not really following along as much as I could. I'll have to like.
If you took the notes earlier, when we started doing the struct, we put some notes there to talk about how we're going to use it.
Yeah, I didn't get it.
Okay, got it. No problem. Volunteer, somebody I haven't heard yet for this morning.
Can I go?
Yeah, definitely.
It's the less than sign.
So angle bracket.
String.
String.
Comma int.
Comma int.
Close bracket.
Close bracket.
And the capacity part.
Capacity 4, right?
That's correct.
Very good. Thank you, sir. And using our examples we had, we could say hash table, the instance of hash table, dot, we could say update value here. Update value, what's the value? Let's say 21, and the string is Tiffany. Okay. So now we added one value. Let's actually see if our count works. So hash table.count. And lastly, just print hash table. So run all that code. Let's see what we have. So hash table string buckets, we have an empty slot here. We have a slot that's taken here, which is index 1. It has Tiffany. We have an age 21. And we have 2 empty slots here. And we have a count of 1. So I'll say this works. Let's try it one. Let's add one more person in. Who else did we have? We had Eric. We said he's 25. And let's run this as well. Here, our count is 2. So we know the count works here. We have Eric. And now you see Eric and we're in the same slot here, Eric and Tiffany. Remember earlier we ran it. Tiffany was in index 1, right? Correct? Or index 2, can't remember. So there's no guarantee for where it's going to be. Again, it's not sorted. There's no guarantee. Every time the hash function runs, it returns a different value. Okay, let us see if remove works here. So hash value, remove value for key. And here the key needs to be the same as in anything else. So if I was to remove Tiffany and print our table again, and print our count as well, print hash table count. Well, here we expect the count to be what?
1.
1. And here, Tiffany's not going to be there. Okay, so run that. Our count is 1, and Tiffany is no longer in our hash table. Before I continue, does everybody have the same outcomes?
Yeah.
Yep.
Yeah, okay, awesome.
Could I take a quick glance at the remove function?
Remove function. So remove, we get the index of the key we're interested in. We go through the buckets. And if we do get the key, then we remove that index. We decrement the count and we return the value. Does yours match up? Oh, you're just missing some parts of it? One, you still with us?
Sorry about that. I got the space bar chat. Yeah, I was missing the count.
Okay,
Thank you.
Got it. Awesome. No, you're welcome. Okay, anything else here that we normally do with dictionaries that would be nice? Like, do we normally do this update value for key thing? I hope not, right? I mean, that's more Objective-C type of syntax, but do we update our dictionaries this way? In Swift?
No.
What do we do? How do we update our dictionaries or access them? I heard no's, but I'm not hearing how do we.
You subscript?
With subscript, right? So we'll do something like this. We'll say HashTable subscript Tiffany equal to 21. Right? Yes? Correct?
Yes.
All right.
Yeah.
But right now, we're getting this error. It has no subscripts, right? So HashTable has no subscripts. So let's fix that. Actually, you could leave your code here. You could comment line 97 out, and let's get line 96 to work, right? Because this is the way we normally do dictionaries. So let's go add subscript in. So right at line 88, we could add a function. It's called subscript. This is built into Swift. We'll return some value. It's optional. That's why our dictionaries are optional. That's why we have to optionally unwrap them or unwrap them before we use them. Our subscript will say for key, or I'll just say key here, and it's just a key. Okay, great. Next, we'll need a getter and we'll need a setter. The getter here will just get the value for that subscript. And the setter is gonna set the value for the dictionary. This is gonna get the value for the dictionary. This is gonna set the value for the dictionary. How do we get a value from our dictionary right now? What function did we write that does that? For our getter here. The getter just returns a value. So it's value, return value, thank you, for key, right? So our getter is done. The getter is this function we just wrote here, value here. Hey, just give us the value for Tiffany. This is gonna return a value. It's optional. All right, very good. Now let's go to the setter. The setter is a bit different. If I set something, I want to check to see if what I'm setting has a value. So here I'll use optional binding. I'll say if let value equal to our setter, very similar to in our did set property observers. There's a new value, there's an old value in our setters here. So in my setter, I want to find out if the new value, does it exist? Is there a value here? If not, then I'm going to remove it. So for my new value, what do I want to do here? Well, how do we add a value to our dictionary right now? What function do we have there? Tanya?
Yes, I'm here.
How do we add? I heard you said it. You said
Still
it.
be update. It's
Update. Yes, update. Very good. So we're here, we'll just call our update. We have a value on line 94, and we have the key. Very good. So if there's no value, that means we want to remove something. Well, we'll just call remove key. That's our subscript. And with that said, we should have no more errors at the bottom where we had an error before, subscripting out our hash table. If we were to go back down, no more errors, because now we do have a subscript function. This is our subscript function right here. You could have multiple subscript functions. So we can have multiple subscript functions. taken in varied arguments based on what you want to do. Okay. All right. So this is what subscripting looks like. On any custom type you could have a subscript if you want to subscript into that object. Okay. Very good. So now we could add Tiffany this way as opposed to this way. And our dictionary should still operate the same. Let me rerun the playgrounds. So here we had Tiffany before, we still have Tiffany here. And then we are able to, well, 117, let's remove that and do it HashTable. Now we want to set Tiffany to nil. So Tiffany equal to nil. So that's what's happening now. So when I say HashTable Tiffany, assign it nil, my subscript gets called, new value, it's nil. So it doesn't come in here, it doesn't do an update, but it goes and it removes the value. Everybody sees that? Yes? Awesome.
Yeah.
So if I was to run it again, and now Tiffany is no longer here, using Swift syntax, right? So, so this is good. So now we have no more update we call in, we're just doing subscripting for everything in our dictionary. And we could use it like we have any other dictionary. We could do things like if let name equal to HashTable some index Alex, like this, print exist, else print does not exist, right? Or we could also do nil coalescent, so we could use optional binding here. We could also use nil coalescent here. So let name equal to HashTable Cameron. Okay, and we could just print name here, and here it doesn't exist. If it does exist, well, name exist. Input type. Well, this is a. Why am I getting an error here? Mr. Bien.
Do you need to assign a value?
Yes, I need to give it some sort of default value, but why am I getting an error here? Before I'm even looking at the error, why am I getting an error here? What am I expecting from Cameron? What's the value?
An integer.
An integer, right? So I'm trying to say, hey, if there's no integer here, well, give it this default integer. Is that an integer? So we have to change this up to an integer. So now that should not be named, that should just be age, and this should be age, and age. Cool. And let's play it now. And now we see it does not exist because there's no name Alex. So it goes into here, same as our dictionaries. And here age, there's no Cameron. So the age is 100, which we have here. So the functionality is, again, very similar to what we normally do in a dictionary. Of course, there's many more things. Dictionary class has, not class, dictionary struct has so many functions on it. We're not gonna write that. There's no point of doing that. But the basic objective was to get us understanding what a hash table is, what's the main vocabulary terms in a dictionary. For example, knowing what a collision is, knowing how to solve a collision, right? Those are the big takeaways here from the actual lecture, okay? Right? And hey, you could probably get asked to implement a hash table. That could be a thing, right? So knowing how to implement all the data structures we've done, including this, is also fair game for any interview as well. Any questions? Any code bugs, anything?
I have a question, Alex.
Yeah.
So, so what we did right now was just we just implemented like a dictionary, right? This is just for our knowledge to understand like how it works.
Yes.
This would be something like.
Say that again.
Okay, yeah, that's it. That's all I wanted to make sure.
How it's implemented, you could be asked the question how to implement a hash table or implement a hash table, right? You could be asked a question, what's a collision? How do you solve collisions?
Okay.
Right, understanding what buckets are, that could be a thing as well. I've seen those being asked on interviews as well. So understanding fundamentally that dictionary is a data structure, and underneath it all, it's a hash table.
Okay.
Okay.
Yeah.
Any other questions, comments, observations?
Oh, yeah.
Yep.
What did we take care of the collision part again in the struct?
So we took care, in the struct here?
Yeah.
We took care of it because we implemented there's the chains right here. So those are the chains here. So collision resolution implemented. Come on. Using chaining. So the bucket, this is an array here. So those are the chains. So this represents. So Sering?
Yeah.
So basically by the nature of the structure we just built, those are the chains.
Okay.
Right? That's why we have to go through and look through them here.
Yeah. I was just wondering, maybe I wasn't paying attention to the chaining part.
No, that's it there. Sometimes you'll see that's like a linked list. You might see a linked list being implemented in different solutions as well.
Yeah.
Right. But here we just use an array.
Okay. Thank you.
Right. No, very welcome. Right. So again, I kept this later in curriculum because now we've seen so many other data structures, and the concept of this makes more sense to us as opposed to like unit 3 showing us what a hash table is. We'll be like, well, okay. But knowing how this works, knowing how to implement it, this could be fair game for an interview, especially, nowadays, right? Any other questions? And along the way, we've seen type alias before, but now we saw setter here, making a setter private. We saw that. Other things we could do here to protect ourselves, we could say assert capacity. Make sure the capacity is greater than 0. Because if it's less than 0, that's no good. We don't want that. So crashes. No. So here we're just asserting that, making sure that the capacity getting passed in is greater than 0, right? If I was to pass in, for example, over here, somebody trying to construct a dictionary with -4 capacity, and I run it. Right, I'll get an error here, right? That error signifies that my assert works because I cannot construct a dictionary if I don't have greater than 0 elements or capacity, okay? So here, just changing that up, we'll get our code to work again. Okay. This is very similar to like your LRU cache problem. That's an edge case. And being careful that if somebody's trying to implement a data structure like that, that takes a capacity, it's almost like protecting yourself against like an array being empty and trying to index into it, right? Somebody's gonna try to create your LRU cache or whatever, or your hash table with like -100 elements or -100 capacity. So being careful for those edge cases there, right? Or being mindful about those.